Let me open a new page and name it complex numbers, and let's see what's going on there. We'll be looking at complex numbers. And there's nothing complex about complex numbers. So please give me the question. I'll note the question down and then quickly go over what you need to be able to answer the question. I'll call it question 1. What were they asking you to do?
So it was, let me just check it right now. I just remember it, not the question. Oh, they said write in modulus argument form.
Okay, so write in modulus and then argument form.
Yes.
And that was the first question, isn't it?
Yes.
And then what was B? So what we were given was in bracket 1 plus I to the power of what? We're given 1 plus I first, and they said we should write in modulus argument form.
1 plus I to the power 10.
10. Okay. So before I answer this question, let me run you over some concepts, and I need you to hold the belt very tight. Everyone in the meeting should put on their seat belts. Let's look at complex numbers and what is going on there, because they are not common. So from metric, you have been dealing with solving quadratic equations. And for example, if I say a solution, if I have 2 plus or minus square root of 4 divided by 2, this would look like something which you would solve back in metric when you are solving for x. However, what we are trying to, or what we are presented with here, is we have never dealt with the square root of negative numbers. So if you take the square root of -1, back in high school, you would say this is very wrong. You would be happy or you would be sad, whoever is taking square root of your negative number, because even your calculator does not know. So all that is going on with complex numbers is we are trying to account for negative square roots, and we call them I, and I is just the root of -1, which is where complex numbers start. So in complex numbers, we have 3 forms. Enough about that, we have 3 forms. So they can come to you and say, write the complex number in real imaginary form. And what is real imaginary form? The complex number will denote it by Z. It will be X plus I, Y. This would be the real imaginary form. Why real imaginary form? Because the X is the real part. And what is multiplying the I, whatever complex number you are given, that is the imaginary part. So when they say write a complex number in real imaginary form, they're expecting you to have X plus IY. For example, e.g., if 5Z is 3 plus 2I, I can clearly see which one is the real part, which is the part which has nothing to do with I. That would be the real part. What is the imaginary part? It is always what is multiplying the I. What is multiplied by the I? This would be the imaginary part. So we are still on real imaginary form. Let's take the last example, e.g., if they give me z is -2 minus 7i. What is the real part here? What is the imaginary part? Anyone? So I'll say the real part of z. That's how we write it, real part of z. So what is the real part of z? Anyone?
-2.
-2, and what is the imaginary part?
-7.
-7, because the imaginary part, it is what is multiplied by I. By the I. And then the real part is what I would call the standalone. It's not, doesn't have any relationship with the I, it's just standing by itself. So they can say right in real imaginary form. Then the second one is modulus argument form. Right, let's go to the next one, which is modulus argument form. And by modulus, all what we mean is magnitude. And then by argument, all what we mean is give me the angle. Okay, and then we need to think now, how do we take the complex number from the real imaginary form to writing it as a modulus argument form? Because when you look carefully, can you see that what we are given here inside is just a real imaginary form? Can you see that?
Yes.
Okay, on point. So now the question which we need to ask ourselves essentially, which we will answer, is how do we move from the real imaginary form to the modulus argument form? That's the question which we are asking indirectly. And if you can be able to do this, then you are good as done. So we'll take x plus iy, because our real imaginary form is always given as x plus iy, and we want to move to the modulus argument form. So the modulus, which is that it will always be the square root of the real part squared plus the imaginary part squared. So this would give you the modulus. So meaning at least you already have something. The modulus is simply the square root of the real part squared, which is x squared, plus the imaginary part squared. That's our modulus. Very important that you are able to find, because we are looking at modulus argument. So now we need to stress about how do you find the angle, and then we plug it back there, and then we finish that problem. So let's look at the argument, which is the angle. So the angle will really depend on where you are. So z is equal to x plus I, y. We are looking at the angle. So I'll draw the Cartesian plane with you. Let me call it the complex plane. We have x and y. So if your x is greater than 0 and your y is greater than 0, your complex number will be in the first quadrant. This will be when your x is greater than 0 and your y is greater than 0, meaning your real part is positive and your imaginary part is also positive. And we are looking for the argument, which is beta. So if you plot your complex number and you see that x is greater than 0 and y is greater than 0, your theta will simply be the arctan of the imaginary part divided by the real part. And this applies in the first quadrant. Okay, and then let's see when we're in the fourth quadrant, what happens. So if you're in the fourth quadrant and you plot your complex number, you find out it is here. Angle theta, when you're in the fourth quadrant, you will see that this can only be, you can be in the fourth quadrant if your real part is greater than 0, meaning it's positive, the x, but the y is negative. So remember, we are still here, x is the real part, and y is the imaginary part. Okay. And then now we're done with the fourth quadrant. On the fourth quadrant, your theta is still that. I need you to be careful. Theta is still the arctan of the imaginary part. Which is just y, then divided by the real part, which is x in our case. And this will apply in the fourth quadrant also. So meaning as long as you're in the fourth quadrant, you just do quadrant. As long as you're in the fourth quadrant, you just do arctan of x, of y over x, sorry. And then when we go to the third quadrant, when we go to the third quadrant, our angle theta will be, now you need to think carefully. So on the third quadrant, and if there's one thing you do not want, your theta should always be between pi and negative pi. If you remember, you know, there's something they call the principal angle or argument. So the formulas which I'm giving you will help you to ensure that your angle is within the principal angle. So meaning, if you follow this, there will be no need for you to reduce the angle and divide into all sorts of things. Okay, so when you go to the third quadrant, on the third quadrant, we know very well that our x is less than 0, meaning the real part is less than 0, and the imaginary part is also less than 0. So our angle theta will be given by our pi minus the arctan of our imaginary part. You put it as it is. Think carefully. Yep, you put it as it is, the imaginary part, which would be y. Then you divide by the real part, which would be x. You put them with their sign, okay, and that would give you the angle on the third quadrant. So this would be the angle on the third quadrant. So let's go to the second quadrant and conclude this here. So second quadrant, here we come. Second quadrant, we should have a complex number looking like that. And on the second quadrant, when we look at the real part, we're expecting it to be negative, but the imaginary part, we're expecting it to be greater than 0. And then on the second quadrant, our theta, which is our argument, very important, will always be given by pi plus the arctan of the imaginary part, which is y, divided by the real part, which is x. Okay, very important. This would be the second quadrant. We are adding pi. So if you can memorize this, this is the second quadrant. You are good to go. So you are done. You are able to find the modulus. You are able to find the principal angle, very important. And that angle must be between pi and negative pi. So now that we know this, let's go back to our problem. So when I look at my problem, I start analyzing it. The real part of that complex number, 1 plus I, is equal to 1. The imaginary part of 1 plus I is whatever which is multiplying the I, which will be 1. And both of these are greater than 0. So the real part, which is x, is greater than 0. And the imaginary part is greater than 0. So if you look carefully, we have x greater than 0 and y greater than 0. And we know this very well that it should be the first quadrant. And in the first quadrant, how do we find our modulus? How do we find our argument? Sorry, it is the arctan of our y over x. So we'll have the arctan of 1 over 1, and we'll have the arctan of 1. You remember the arctan of 1 is 45, but we are working in radians, so 45 is pi over 4. And this would be our famous argument. Okay, and then now we need to find our modulus. When we look at our modulus, we can see that the real part is 1, the imaginary part is 1. And modulus is given by the square root of the real part squared plus the y, the imaginary part squared. So this will be the square root of 1 squared plus 1 squared, which will be square root of 2. So we now have our argument there, and we have our modulus here. So the answer, or when we write 1 plus I in modulus, in argument modulus form, it will simply be equal to square root 2 at an angle of pi over 4. But remember that sine and cos are periodic with period 2 pi k. So we can put 2 pi k. So this would be on the left-hand side. This would be the argument or the modulus argument form. And then on the left-hand side, it will be the real imaginary form. Okay, but then what we see is that we have a power, we have to the power of 10 there. So we need to deal with that. So let's take that and then raise the left-hand side and the right-hand side to the power of 10. Do we still follow the person who posed the question? Are you still understanding? The person who posed the question, are you still there?
Yes, sir.
You follow? Get a page and raise it to the power of 10 and give them the final answer. Paste that there. So what I need you to remember is that this here, when we write in Euler form, that there is the angle and that there is the R. So that's the angle theta. So in Euler form, what we have as our Z is always R e to the I theta. So it becomes easy if I move to Euler form, then back to modulus argument form. But sometimes they call this here also modulus argument, because we have the modulus and the argument. So our R is our modulus, which is equal to 2e to the I to the power of pi over 4 plus my 2 pi k. And then if you look carefully, they had raised this to all of this to the power of 10, which is what we need to do and complete the question. So this was 1 plus I, but I need to put the power of 10. What I do on the left, I do on the right, in a 10. So when I put in the 10, you will see that we'll have square root 2 to the power of 10, and then EI. The 10, when it goes to the exponential part, it multiplies. Okay, so that means we will have 10 pi over 4 plus 20 pi k. And then when we take the square root, or when we do the square root of 2 to the power of 10, you should remember that square root is just to the power of half. That's what a square root is. It is to the power of half. So I can put in my 10, and then my e to the I. What I can do there is I can try and simplify this and have a 2, so that I will have 5 pi over 2, and then plus 20 pi k. Right, and then when we quickly solve that, the 10 will multiply the half, it will be 2 to the 5. And then the e, remember Euler's form, we can take back to the real part form. So they said the final answer should be in what? Modulus argument form.
Yes.
Okay, so this is our modulus there after applying the 10, and then our angle is all what is up there. So our angle is 5 pi over 2, and then plus our 20 pi k. Do you have any questions?
Oh, so the answer had cosine sign, so that Euler form to the other one.
Yes, so what we were supposed to do is, you know that e to the I theta is cos theta plus I sine theta. So it means they wrote it in what you call real imaginary form, the final answer. So we'll have 2 to the 5, open bracket. When you look at this part here, we can clearly see that all of that is our theta. So which means we should have cos of our 5 pi over 2 plus 20 pi k, and then plus I sine of 5 pi over 2 plus 20 pi k. And if you remember, sine and cos are periodic with period 2 pi k. So as long as whatever we have is a multiple of 2 pi k, then it becomes the original signal itself. So we'll have 2 to the 5, open bracket, cos of 5 pi over 2 plus I sine of 5 pi over 2. Is this what they gave you?
Yes, but the answer was pi over 2. And my phone is gonna switch off.
Okay, so the answer was pi over 2. So we need to reduce this into our special angles, which we know. So let's quickly see how can we reduce 5 pi over 2 to something which we know. So let's look at 5 pi over 2. For 5 pi over 2, we can write it as 4 pi, I think 4 pi over 2 plus pi over 2. Let's see, is this true? Yes, it is. So if you look carefully, what we have is simply 2 pi plus pi over 2. And this looks like something which we can deal with, because 2 pi, we know it's like adding 360. So that means our answer will become 2 to the 5 cos of, think of it as 360, because 2 pi is 360, plus 90, plus I sine of 2 pi plus pi over 2. So if you remember, your cos of 360 plus any angle is cos of that angle. Same goes for sine. Sine of 360 degrees plus any angle is sine of theta. And remember that 2 pi is equivalent to 360 degrees, 2 pi radians. So our answer should be 2 to the 5, open bracket, cos of pi over 2. We all know what cos of 90 is, plus I sine of pi over 2. We all know what sine of 90 is. Cos of 90, we all know it is 0. And then sine of 90, we all know it is 1. So the 1 will multiply the I, so we'll end up with 2 to the 5 I. And 2 to the 5 is 32. Are you answered?
Yes, thank you so much.
So this would be 32I. So please, all in the meeting, make sure that this diagram here, which I have, you will sleep knowing how it looks, because it will make your life easy when you want to raise complex numbers to powers and do all sorts of things. It's very important that you are able to find the principal angle, which is the angle which is between pi and negative pi. How do you find it? You use exactly what I gave you above here, all these details. Depending on the quadrants, if you apply them right, you will get the principal angle. Anyone in the meeting who has a question? And this here also, Euler form or Euler relationship, it is very important. Anyone in the meeting who has a question? Very short questions. People have been trying to come in. Okay, they're all in. You. Okay, no problem. Let me pause this one once again and then see if